Okay, so let me welcome everyone, and let me say that today we are very happy to have Professor Sergei Gukov from Caltech, and he's going to tell us about higher form symmetries in TQFTs and Coulomb branches. Over to you, Sergei.
Yes, thank you so much to everyone, to the organizers for putting this meeting together and their hard work despite all the difficulties and challenges that we're facing, including the technical ones. I also want to thank Abhijit for stepping in and hosting me. This is actually my second time visiting India in the last couple of months, and Abhijit is being the host, both of them, so it's a pleasure, and I hope to come back, hopefully in the near future. So what I'll tell you about in this half an hour or so is snippets of work that we've been doing with various collaborators, and it's mostly based on these two recent papers, which share mathematical content. It's roughly half of the work, and today I'll focus on the other half, which is for today will be exclusively physics component, and some of the collaborators here are split among physicists and mathematicians also fairly evenly. So for instance, in our physics community, you probably know many faces, even mathematicians such as Hirako Nakajima. Probably less known to you is Francois Costantino, who is an expert on fairly exotic so-called non-semi-simple TQFTs, which until recently had not really appeared in string theory or quantum field theory community. And these two papers are basically devoted to bringing this kind of TQFTs in light. And I'll try to explain why they're interesting or delicate, even from the TQFT point of view. So the main theme of the talk will be symmetries, and symmetries will play a sort of double role in this talk. So they'll be very important for solving certain problem or helping us with a certain issue. That's one aspect. But in the same time, symmetries will make certain things delicate and more interesting. So on the one hand, they'll come and solve for a certain problem, but on the other hand, they'll introduce additional layer of complexity, which in my opinion is not really complexity, but makes story richer, more interesting. And keep in mind this two roles that symmetry will play in this talk. And the other, or physics goal of the talk in some sense, is to understand superconformal field theories. In my case, it will be three-dimensional and equals four theories, but could be something more general, for example, 4D superconformal field theories or 2D superconformal field theories via their moduli spaces. The most popular types of moduli spaces of vacua involve Higgs branches and Coulomb branches, parameterized respectively by either vevs of matter fields or fields in supermultiplets for gauge field SIDS. And these are Higgs branches and Coulomb branches, which in three dimensions also split their role in a way that Higgs branch is typically simpler, especially with this amount of supersymmetry, whereas Coulomb branch still remains delicate and interesting. For instance, chiral ring of operators on the Coulomb branch and such theories involve monopole operators, which is one of the most interesting aspects in this kind of theories. And the goal is to understand, first of all, Coulomb branch, and then use information about these branches to sort of bootstrap or say something about strongly interacting conformal field theories. That's the motivation. But even Coulomb branch itself often turns out to be quite interesting and delicate, and there are several ways to deal with this issue. One is to seek various dualities which map Coulomb branches into Higgs branches of different theories. This is known as three-dimensional mirror symmetry. Or try to tackle strong coupling effects which are protected by supersymmetry. For example, one can try to explore these monopole operators, study the chiral ring in general, and this gives information about this moduli space, the Coulomb branch M, via basically accessing its coordinate ring of holomorphic functions, or if you prefer to work with some function or number rather than space, you can ask about the Hilbert series. So that's a simple kind of function that encodes information about the Keil ring, and it was actively studied in many recent years. For example, by Ami Hanani and collaborators and by various other groups. So developing various techniques how to compute, for instance, either coordinate ring or the Hilbert series. So this is the basic information about the Coulomb branch, and this is going to be the star of the show in the rest of the talk. One aspect which from physics point of view is completely obvious and does not deserve much time or attention is the fact that Coulomb branch is always non-compact. So this doesn't present any question from physics point of view, but in a moment it will present, it will be important. It will present a certain technical difficulty. So the point is that to every Coulomb branch, or more generally moduli space with the same properties as such Coulomb branches of 3D n equals 4 theories, you can associate a three-dimensional TQFT. So that in that same 3 dimensions where we discuss our 3D n equals 4 superconformal theory. And in that TQFT, these two ingredients, namely the ring of functions on a Coulomb branch as well as its Hilbert series, appear as basic building blocks. Namely, the Hilbert space on a sphere is exactly this ring of holomorphic functions, and invariant associated to S1 cross S2, roughly the trace over this Hilbert space, is precisely the Hilbert series of the Coulomb branch. So the fact that in this three-dimensional TQFT, Hilbert space on a two-sphere is a commutative ring is fairly easy to see by visualizing the following. So you think about two-sphere to which this Hilbert space is associated, and construct a big three-dimensional ball from which you excavate two smaller three-dimensional balls. Then what it does, it provides a map from two copies of the Hilbert space of a two-sphere, because there are two boundaries inside, to another one, and that's exactly the product in this commutative ring. And it's also commutative because you can interchange these two smaller spheres, and their order does not really matter. So that's how you see the commutative ring structure. Now, we mentioned a moment ago that Coulomb branches are always non-compact, and this will lead to interesting feature of these three-dimensional TQFTs to be, on the one hand, not quite TQFTs in a standard sense. They'll be funny, or more technical name is logarithmic, that already showed up on the first slide. And in the same time, symmetries will play an important role. So they'll be decorated or enriched in the terms of condensed matter physics by additional symmetries. So any questions so far? Okay, if not, I'll proceed. So the three-dimensional TQFT that I have in mind in the previous slide is a theory introduced by Rosansky and Witten. So they proposed how to make a three-dimensional twist of such 3D n equals 4 theories. And the twist leads to precisely the properties I mentioned on the previous slide. In fact, the moduli space did not have to be a Coulomb branch. It could be a general hyperkähler manifold, or even more generally, some holomorphic symplectic manifold. But for today, think of it as a three-dimensional Coulomb branch, which is going to be useful for many things I'll try to say later. This topological quantum field theory is mathematically well defined. So shortly after the work of Rosansky and Witten, it was formalized by Kontsevich, and also independently by Misha Kapranov, who used IT classes. So now this three-dimensional TQFT also exists in a strict mathematical sense. However, it exists for compact target spaces or compact manifolds. So here, Rosansky and Witten call moduli space by capital X. So I'm going to adopt their notations. And when X is compact, such as K3, for example, everything is fine. And that's indeed where we have this mathematically rigorous definition. But throughout the paper, Razansky and Witten point out a number of times that when X is non-compact, we have to be extremely cautious. And in particular, if we try to study this Hilbert space that I mentioned before, associated to various surfaces of various genus in this TQFT, then analysis could be hazardous at best if X is non-compact. And that's exactly the issue that we're going to deal with in this talk. So that's the catch. So on the one hand, Coulomb branches of such theories are always non-compact, and therefore it seems like an important challenge to tackle. So here is an explicit form of the Hilbert space, also taken from their paper. Here you can see very explicitly that indeed, for example, for two-sphere, when we ask for Hilbert space of this TQFT on a two-sphere, it's simply a space of holomorphic functions on the Coulomb branch, and more generally space of holomorphic forms. But again, if a Coulomb branch is non-compact, that's going to be infinite dimensional space. So that's the problem. That's the challenge.
Sorry, Sergey, what is V in this slide?
V here is, I believe that, yeah, so here is a holomorphic tangent bundle of X. Yeah.
Thanks.
Yeah, sorry. Yeah. I just literally copied the formulae from their paper. Thank you. So another player that will somehow show up later in the talk is modular structure. It's not going to be as important as symmetries or other ingredients I mentioned, but this is something that's good to keep in mind, especially in connection to two-dimensional conformal field theory. So the reason is that in the case of theory like Chern-Simons theory, for example, the dimension of the Hilbert space on a genus G surface is closely related, and in fact can be expressed in terms of modular data, so-called S metrics of the corresponding two-dimensional CFT. So that's a famous Verlinde formula. And the same procedure works for many three-dimensional TQFTs whose Hilbert space on genus G surface is finite dimensional. This is a fairly general phenomenon. You can associate modular data to three-dimensional TQFT, and therefore S metrics will show up and encode dimension of the Hilbert space. But the situation that we're dealing with involves infinite dimensional Hilbert space, as we just saw a moment ago in our three-dimensional TQFT. So a natural question will be, what's the analog of this Verlinde formula? We can't literally just take the dimension of it because we'll get infinity. So we'll have to regularize it in some form. And I don't know how to answer this challenge posed by non-compactness of the Coulomb branch in general, but what I'm going to propose in this talk, based on this work with Nakajima and others, is to use symmetries to consider equivariant version of this regularized sum. So this will provide regularization, and it's true that Hilbert space will be infinite dimensional, but as long as there is a symmetry that allows to split it in finite dimensional graded pieces, then we can form this series introducing corresponding equivariant parameters. I'll call them T, X, and so on in the rest of this talk. So they will provide additional grading and will allow us to write infinity in a nice way as a power series in terms of this equivariant parameter T. So this trick goes back at least to work of Moore, Nekrasov, and Chatashvili, where they used equivariant integration over Higgs branches. So what we'll be doing is a basically Coulomb branch version of that. And many other works before we implemented it with DU in exactly this sort of context that will be relevant to us. These days, similar equivariant regularization is also used in many other TQFTs in other dimensions whenever the Hilbert space turns out to be non-compact. For instance, in the work of Tanaka and Thomas, it's used to regularize ୱାffle-Witten partition functions. It can be used to regularize multi-monopole Seiberg-Witten systems in 4-dimensional TQFT based on this multi-monopole equations and so on. So symmetry will be of our help here. And the formula that we propose for analog of the modular data, where the sum over this labels lambda is still going to be a finite sum, is such that given a Coulomb branch, which again, following Rosansky and Witten, I'll call X, the claim is that the sum can be still expressed in terms of finite dimensional data of fixed points. So I'm going to denote fixed points of symmetry. Let's say there is a U1 symmetry, it could be larger in general, acting on the Coulomb branch. So lambda will be labeling the fixed points, and then geometric data at a fixed point will determine the matrix elements of T matrix and S matrix, very much like in the usual modular tensor category or modular data of conformal field theory, so that you can use this data now to produce this equivariant version of Verlinde formula or invariance of 3 manifolds. And once you have a symmetry, let's say U1 symmetry with the equivariant parameter T, a general holomorphic symmetry acting on such Coulomb branch will have, first of all, moment map, because it's Hamiltonian, so a moment map I'll denote by mu, and it also acts with various weights and normal bundle directions. So assuming that fixed point is isolated, for example, you'll have lots of the whole vector of weights, W, and this information of W and mu determines essentially enters this matrix element. So the W's enter denominator of this formula, mu, for example, enters the matrix element of the T matrix, and so on and so forth. You can find further details on how to associate additional data in those papers I mentioned. But I want to focus rather on examples, especially since time is short. So,
Sergei, I apologize. Can I just ask this? What you have is square root kx. It's like is a square root of a canonical bundle? I mean, do you have some kind of a spinner in the story?
Well, yes, it's a square root of canonical bundle of this non-compact target space or Coulomb branch X. Yeah.
So I mean, right. Section. So that would be some spinorial degrees of freedom in your story.
That's correct. In fact, in general, this formula that I'm presenting here, obtained by summing over lambda of this expression, is nothing but counting index of the spin C Dirac operator on target space on this Coulomb branch X. That's correct.
Oh, okay. Thank you so much. Thanks.
Yeah. That's maybe another way to think about it. So instead of, again, outlining the general story and give you further details, let me give you a couple of examples. So hoping that will shed light. So in this first example is where X has hyperkähler dimension 1. So it's a fairly small dimensional manifold with U1 symmetry. With respect to the symmetry, it has 2 fixed points. So there will be the size of this S and T matrices will be 2 by 2. Here is the values of the moment map and the weights for these 2 fixed points, and all these fractions of 1/5 or 6/5 and so on translate into specific elements of S and T using the rules on the previous slide. And what you get is S and T matrices of Fibonacci anyons. So that's one simple example that comes from 3-dimensional reduction of a 4-dimensional Argyris-Douglas theory. Well, if you think about hyperkähler manifolds, this choice of X is not the simplest one. In fact, the simplest one probably that would come to your mind of this smallest dimension would be cotangent bundle to CP1. But this one is actually more interesting and more complicated because the example that leads to this Fibonacci anyons is more generic in a sense. In particular, the weights are fractional. It has only 1 symmetry, whereas T star of CP1 has actually 2 symmetries. And that's going to be important in the rest. One is holomorphic, that's what I just used, that's kind of generic, but the other is a little bit more special. It's holomorphic with respect to all three complex structures or symplectic structures. And again, there are two fixed points, north and south pole of CP1. So in that sense, it's similar to the previous example. If you work out the normal bundle weights and all the moment maps and everything, you get these values, for example, for the S matrix and similar for the T matrix. So you put it together and you can compute this regularized TQFT, Rosansky-Witten TQFT invariant associated with non-compact space T star CP1 on any genus G surface, in particular on S1 cross S2, which is indeed supposed to be the Hilbert series of T star CP1. So T star CP1 can be presented in many different ways, for example, as a quadric and so on. And you can easily compute its Hilbert series, so indeed it will match this expression. But important difference between this two symmetries, one of which is just holomorphic and the other is actually triholomorphic, is that the holomorphic one cannot be consistent with topological twist on a general three manifold, whereas triholomorphic can. So when you go to more general three manifolds and use these ingredients, for example, of modular data, S and T matrices, you can compute using this S and T matrices invariance of more general three manifolds, but you're obligated to remove variable T, set it to 1. But you can actually still keep variable X on a general three manifold, and then question becomes, what is X? So it turns out that it's playing a very important role. So it's additional decoration of the TQFT. So it's additional structure associated with the symmetry. And if you go through all the details of this twist, you see that it's actually background for higher form symmetry, namely one form symmetry, or even more precisely for so-called spin C structure on the three manifold. So it's labeled by elements of H upper 2 of the three manifold. So that's the crucial difference between the two symmetries that you could use. And from regularization point of view, both of them would be helpful, but one can survive on a general three manifold, but the other cannot. So this, you can continue playing with many other examples. Of course, I showed you the simplest ones like T star CP1. Of course, you can consider cotangent bundles to Grassmannians, Hilbert schemes of points, and various other interesting metrics, hyperkähler metrics on non-compact manifolds. So all of them correspond to interesting TQFTs, but all of them are non-compact and will require some kind of regularization, which will force us to think about TQFTs, which are not quite usual TQFTs. In fact, they're logarithmic, but they're also equipped with a more general symmetries and structures, very much like this variable X, which showed up a moment ago. And what we're seeing here is in this talk a kind of dictionary or relation between geometry of Coulomb branches and algebraic structures that appear in a TQFT. So I already mentioned modular tensor category. That's something that you can associate to every TQFT, and it's describing braiding and modular data of anyons. And this tensor category also can be realized as a representation category of some vertex algebra or conformal field theories. And what's interesting in examples that arise from such Coulomb branches is that corresponding MTCs are non-semisimple, and the vertex algebras or CFTs are logarithmic. So that's rather interesting exotic feature of this correspondence. So in the remaining 3 minutes, I hope Chair allows me 3 minutes. I want to go through and I say a few words about the role of this decoration, this additional data that arose from a symmetry that we used in order to regularize partition functions. So this background data or structure associated with the symmetry goes by many different names in the literature. And it's interesting that these names or structures are not really aligned, and people from different walks of life didn't compare, at least until so far, some of these backgrounds or terms that appear in the literature. And from the CFT point of view, we're simply talking about twisted sectors, where we consider vertex operators labeled not only by position on a plane and choice of operator, but also by an element of the group, such as G1, G2, and so on. And from the three-dimensional TQFT, this corresponds to labeling line operators in addition to usual labels by choice of symmetry. So to illustrate what this means, in this recent paper with Francois and Pavel, we discussed a very simple example as a warm-up. So just usual familiar U1 level K Chern-Simons theory. So this theory has usual zero form symmetry, nothing fancy yet, just zero form symmetry U1 or C star if you prefer to work with holomorphic in a holomorphic setting. And the symmetry is simply described by connection, background connection, which couples to the first Chern class of the U1 gauge bundle. So C1 is the first Chern class of gauge bundle, omega is a choice of H1 on a 3-manifold, and here it's valued in G because that's our symmetry. Important point from TQFT point of view is that Hilbert space in such setting is first of all decorated by this symmetry. So for instance, if your surface is sigma, then you have to choose elements of H1 of sigma with values in this symmetry group G. But in order to ensure cutting and gluing properly, you also have to consider additional structure from H2 of sigma. And that's additional grading, which involves Pontryagin dual G hat of the symmetry group, in our case, U1. So this example is extremely simple, and of course it's a free theory, but it's very illustrative for generalizations. So here in this three-dimensional TQFT, the category of line operators for any choice of group element G has K objects. So there are K lines in U1 level K Chern-Simons, but when things are twisted by this G, these charges of line operators are shifted, and line operators themselves, even though they define in the usual way, they're always attached to the boundary of a surface operator, which becomes, if you try to run this line operator into the boundary, the usual twist operator in the from the twisted sector, in this case, G twisted sector of the corresponding boundary condition. So this is going to be the last slide. So just to summarize, I explain a little bit how this G symmetry shows up in TQFT. It provides very delicate and important information of decoration and grading for Hilbert spaces and plays an important role of cutting and gluing, which I didn't have time to discuss. But what we saw earlier is actually analog of this for one form symmetry, which is closest to this spin C structure that emerged from using triholomorphic symmetries in Coulomb branches. And this likewise gives rise to additional data of decorations and gradings where degrees are shifted the way you'd probably expect it to be. But again, Pontryagin dual shows up and plays a role. And the reason we needed this analysis and go down the rabbit hole of analyzing the symmetries is because we encountered a relation between TQFTs, which on the one hand are decorated by H1 elements and correspond to the usual zero form symmetry, just like in U1 level K Chern-Simons that I showed. But on the other hand, they're related to this spin C decorated TQFTs, and relation between them involves a version of Fourier transform, which changes degrees of these forms on the slide, but also involves spin structure on one hand, but not on the other. So this is basically a version of Bosonization in the world of TQFTs. So that's the real application why we needed this. And I want to thank you for your attention. And yeah, thank you.
Thank you very much, Sergei, for a wonderful talk. So let me ask if we do have a couple more minutes. So let me see if people have any questions. Yeah, Alok, go ahead, please.
Yeah, hi, Sergei. I just have a very general question. So if you look at moduli space of flat bundles with non-compact gauge group. I mean, can some of the ideas you described be used to quantize it in the in your initial part of the talk?
Yes, that's yeah. Yeah, hello. So that and thanks for this question. The short answer is yes. In fact, the idea here in this equivariant regularization of Hilbert spaces that led later to equivariant Verlinde formula and many parallel developments is precisely indeed aimed to develop the rules of cutting and gluing into QFTs where, for instance, the Hilbert space comes from quantizing non-compact phase space or moduli space of some connections or structures which is intrinsically non-compact. So the idea in such approach or such setting is typically to understand very well how things behave on S1 cross-Riemann surface.
Yes.
And once this is done, so once you have this sort of equivariant Verlinde formula under control, you can actually proceed to talk about S and T elements. And this already is the door to most general modular tensor category, which relies on this modular data. Yeah.
Thank you. Abhijit, can I just ask a small follow-up?
Sure, please.
So in the case of the moduli space for the compact gauge group, we have this idea that index of the Dirac operator is the quantization, right? So is there a similar interpretation if I did, if I quantize moduli space of flat bundles on a Riemann surface with boundaries, but with non-compact gauge group? The fact that quantization is the index of the spin C Dirac operator.
Yeah, I think it's good, at least to first approximation, you can think that it's very similar. The only question is that now formally this index will be infinite dimensional. For example, if you think mathematically about the index as virtual space, vector space, or complex, this complex is going to be infinite dimensional. So that's why the symmetry is important. It's providing additional grading to this infinite.
I see. It just splits the sum into the infinite sum into the sector.
Yeah, exactly. It splits into finite dimensional pieces. Of course, there are infinitely many of them, but as long as each piece is finite dimensional, we're in a good shape. So that's the idea. Yeah.
Okay, thank you.
Okay, so before we move on to the next speaker, let me ask a small question. So, Sergei, people sometimes couple non-dynamical sectors to non-topological sectors to topological theories, such as in talking about Chern-Simons matter theories. So, can such a thing be done in this context?
That's a very good question. So usually, right. So they probably do it most of the time in the case where ambient background is flat, so we consider something basically as a flat space, because as you say, the other sector is non-topological, so it's probably better to consider it just in flat space. Or
the sphere also, for example, people consider.
Yeah, on special, rather simple free manifold. Yeah, so that's a very good question. I don't know if coupling to such, so that's true. Examples like I've seen, for example, in the case of duality appetizer and simple theories like that, one usually finds a coupling to rather simple TQFT, which is quote unquote small. So it's a very light, simple thing. So these TQFTs I described here today are very heavy in the sense that they have infinite dimensional Hilbert spaces. So I haven't seen such an example, and it's an interesting question. It would be good to either find it or maybe even construct and see what happens, because I don't think we have experience of coupling this sort of TQFTs to usual QFTs.
Right.
Yeah, very, very good question. I have no good answer, but worth exploring.
Thank you. Okay, so at this juncture, let me request the original scheduled chair of the session to take over. Please, Professor Ramadevi, over to you. And I will also, sorry, go ahead. You are on mute, Rama.
Yeah, I don't know. The Zoom didn't connect at 9:25, and now I rebooted my machine. It's connecting me to a different background. I don't know in which country I am and which city I am. Are you all able to see me in a different background? I really don't.
It's a lovely background. Given the winter here, it's very refreshing to see that.
I'm sorry. I don't know. The network really bothered me. Anyway, now I'm fine. Yeah, thanks, Sergey. I missed the initial parts of your talk. Probably I saw the last 20-25 minutes. I had a small question. The sigma g cross S1 partition function, has anybody done the large N expansion and written like the 2ft expansion? Anyone has done this?
Yes, I think questions like this come up in the study of ADS4 black holes.
Like about 20 years ago, I struggled a lot, but I didn't fix it. So
Yeah, right. Now I think it's yes, it's being explored, at least in some cases. Typically with simpler versions of these TQFTs, and again, they don't really require very general 3 manifolds as backgrounds, but 3 manifolds that are natural in the context of ADS4 black holes. So in that case, one can indeed consider such partition functions and study large N expansion. Yeah.
So those days, the Vipul Periwal had a neat expansion for sigma 1 cross S1. But yeah, so for a sigma g cross S1, I struggled a bit, but I have not still succeeded. Maybe I'll take a look at these references.
Yeah, I think in general, in this context, there is a lot to be done, even with large N expansion and exploring some of these more exotic theories with logarithmic MTCs or symmetries. So such exotic TQFTs, for example, they didn't propagate into our QFT world until recently. So I think there is more to be done. But I also don't want to delay the session further, so maybe
yeah, we can.
I'll be glad to answer questions over email as well.
Yeah, sure. Anybody else has any questions? Otherwise, we can thank Sergey again for this nice talk, and we can. Anyone else? I'm missing.